Okay, I'm sorry, students. I'm a bit late because of some technical glitches. Live stream was not available. I'm really sorry. Okay, let's begin. I hope I'm audible and visible. Okay, let's begin with the non-linear data structure graph. See, in case of graph, we can consider a graph as a non-linear data structure which consists of edges, set of edges and set of vertices. Okay. So, whenever we are talking about any nonlinear data structure, we are talking about tree, graph, etc. So, in case of graph, we are having set of edges and set of vertices. Graph are represented with G of VE. Okay, thank you Shoham for responding. I'm very sorry that I'm a bit late. Actually, por class zero, that's why it got a bit puzzled. Okay, graph is consist of set of V and E. V is denoted for vertices and E is denoted for edges. V of G means set of vertices and set of edges is denoted by E of G, and they are interconnected among them. See, this is an example of graph. See, the A, B, C, D, E are the vertices and A, D, these are the edges, A, D, A, B, and this is also an undirected graph. Why it is undirected? See, there is no particular direction. We can use one edge for both, for any set of two vertices. Any set of two vertices, we can use one edge. We can go from A to B and B to A. We can use this same path as well. But in case of directed graph, we cannot use the same path like this. A to B, we are having this edge A to B, and for B to A, we cannot go with this edge because this is directed. This arrow is denoted with the direction. Can only be used from A to B. This is why it is called a directed graph. Maybe we can use this path to go from B to A, like B, D, A. But there is no direct edge from B to A. But there is one edge between A to B which is having a direction from A to B. So, that is the directed graph. There will be a direction, okay, for every edge. So, basic terminologies are there: path, closed path, cycle, connected graph, complete graph and weighted graph. Let me tell you one by one. See, previously I have taken the same class. There are videos, so you can watch them also. So, see, for any graph, path is like between any two vertices. If we traverse, suppose A, B, C, A to B, B to C, this is a path. Again, suppose A, B, D, A, this is also a path. Suppose A, B, D, only A, B, D, this is a path. Okay, A, B, C, E, this is also a path. Any kind of traversing from one vertex to another one, which is possible with the direction. If it is undirected, there is no need of worrying of, traversing, because we can traverse anywhere we want. But if it is not, it is directed, then we have to, follow one thing, that you have to be very careful about the traversing where you are going, okay, and any kind of this traversing is called a path. Now, the closed path. What is a closed path? Closed path means any kind of edge is repeated. Suppose A, B, D, A, B. This edge and vertices are repeated. A and B is repeated twice. So, edge and vertices are repeated in closed path, and if A, B, D, A only vertex are repeating, that is called a cycle. So, what is the difference between a cycle and a closed path? In a cycle, we can have repeating vertex, not edges. In a edge, in a closed path, we can have repeating edge as well as repeating cycles. Okay. Finally, this is the graph terminology. Okay, now we come to connected graph. Which one is connected graph? If there is any secluded vertex, like this is a connected graph, all the vertex and edges, there is a connection between them, at least with one edge that they are connected, all the vertex are connected at least with one edge. But if there is a pendant vertices over here, f, suppose here, but there is no connection with any edge, with any vertex, so that will be called a disconnected graph. Okay, and this is a connected graph. And what is a weighted graph? I will get back to you, but first of all we need to know a complete graph. See, if there is any edge between any two set of vertices, for every two set of vertices for a graph, that will be called a complete graph. Suppose this one, this is having two vertices and there is one edge between these two. This is having three vertices. If we consider these two, this is having edge. If we consider these two, this is having an edge. So every set of two vertices is having edge. Okay, so that is what we called a complete graph. Is it clear? Is it if it's not clear, I'm repeating. Okay, for complete graph, we are having, for any two vertices there will be an edge, any two. For these graphs, we are considering these as complete graph. If we consider any two vertex, we are having edges, right? Fine. Okay, now I am moving forward. Okay, okay. So how can we represent graph? How can we represent graph? See, with adjacency matrix and list also. First we will see the adjacency matrix, then we'll see the adjacency list. Okay, first of all, if there is any edge, in case of adjacency matrix I am telling, if there is an undirected graph and if there is any edge between them, between the two vertices, we'll put 1. Suppose here A to A there is no edge, cool. A to B there is an edge, so 1 is there. B to C there is an edge, B to C, 1. We have to put all the vertex name here and here also, row wise and column wise, and then we have to check if there is any way, path or not, edge or not, and we'll put 1 or 0 according to that. In case of undirected graph, what we have to do is, if there is an edge between A and B, so we have to consider there is an edge between B and A also, because we can traverse in both ways. But if it's a directed graph, like this, if there is an edge between A and B, that is not necessary that we have to put an edge between B and A, because there is no direct edge between B and A. So for A and B it is 1, but for B and A it is 0. Clear? For A and B it is 1 and for B and A it is 0. So this is how it's represented. We have to follow the direct edge and we have to follow the direction in case of directed graph. We don't have to follow the direction in case of undirected graph. Okay. If we represent it with list, okay. Next one is weighted graph. Everybody has asked about the weighted graph. The weighted graph itself is the weight of the edges. Okay, these are the weight cost assigned for any edge. Suppose A to B, 4 cost is taking. Cost 4 is taking. We have to put, instead of 1, we will put 4 here. Okay, that is the main difference. Otherwise, it's same as adjacency matrix. Just put the weight instead of 1 and 0. Put the weight if there is an edge. A to B there is an edge, yes, 1, but there is a weight, that's why we are putting the weight over here. This is how the adjacency matrix is defined by the weighted graph, and this is the weighted graph. Weighted directed graph. Weighted undirected graph happens all as well. So, we will move to the adjacency list. Okay. If it's not clear, please let me know in the chat box. Okay. So, we will consider the adjacency list. See, we will check the neighbors. First, we will start with node A. It has only one neighbor, B. So, we are what is the function of matrix here? We are representing it in the computer memory for graph. Graphs are represented, graph can't be represented like this, right? Like this, they can't be represented. We have to find out a way of representation. Matrix can be represented in memory, computer memory, as well list also can be represented in computer memory. That's why we are using list and matrix for graph representation. Okay. Weighted graph, suppose we are telling you to, travel from Shialda to Newtown. Okay. So, there will be some cost you need to find out. If a delivery boy is delivering some delivery items to some customers, okay, the customers lived in several places. He has to calculate the total cost over all the places. Then he has to tell the company over here, over there, that I have to take this much money or this much petrol to buy to travel all the places. The minimum one he has to consider. How he can consider this? To calculate the weights, the costs he can calculate. Okay, the costs are like this, he can calculate. The costs are like how much time or effort or money it will take. Graphs are basically related to our real life. If we have to traverse in several places, we have to consider the graph. Okay, that's why weighted graphs are here. And there are more functions of weighted graph which we will know later on. Okay, next classes. Now we are moving to the next thing, that is adjacency list. If A is having one neighbor, we are putting B here, and the next pointer is null. A is not having any more neighbor, that's why it is null. Just remember the linked list. Okay, the linked list is like that only. The linked list, what it contains, the node, in the node the data part is there, and then the address of the next node is there. There's a pointer part and the data part. Similarly, in adjacency list also, if A is the beginning vertex, it will contain the data of the node, neighbor node. So, it is containing the link of the neighbor node, one neighbor node, and then it will contain the further neighbors. The next node will contain the further neighbors. For B, in case of B, we can understand it. In case of B, B is having two nodes as its neighbors. So, for B, B to C and C to D. Okay, B to C and C to D. And for no more further neighbors are there. That's why in case of D, we are putting null over here. Okay, this is adjacency list. I hope it's clear. Okay, this is the linked representation. Same thing. This was directed and this is undirected. I have told you already that in case of undirected graph, what it does is, if there is a path between A and B, then there will be a path between B and A also. Okay, clear? Fine. Next one is, in case of weighted graph, what we have to do is, in case of weighted graph, we just have to put two parts in the node. One will be the name of the node, that is B or C or E, whatever, and one will be the cost or weight of the edge. Here in this weighted graph, every edge has a particular weight, 5, 7, 8, that are put in the middle place, and if they are having any further node, that will be continued or it will be put null. This is how representation of weighted graph is done. Okay. So, I hope it's clear. If there is anything, feel free to ask me. Okay. This is the graph. There are two graph traversal algorithms. Why we need to traverse the graphs? See, we have to follow two kind of traversal to visit each and every node. Okay, examining all the nodes and vertices of the graphs. Okay, two standards methods are there. One is breadth first search and second one is depth first search. I'll directly go to the BFS example, breadth first search example, so that you can understand the algorithm, how it works. Okay, just follow me so that you can understand. This is a graph. We will put an adjacency list. First, we will create an adjacency list. This is a adjacency list. How we will create adjacency list? For A, there are two neighbors. This is a directed graph. So, we will consider the direction also. Direct edge and direction. Neighbor will be considered which has the direct edge. They are only the neighbors. Okay, not maybe we can traverse. Suppose we are going to from Howrah to Shialda. If there is a direct bus, one bus which can traverse from Howrah to Shialda, that means Howrah and Shialda is neighbors. If there is no one bus, we have to break journey. We have to say, get down on College Street. Then we have to take another bus. Then it is not neighbor. Okay, same thing happens with the graph. Okay, so if we are traversing from A to B, there is a direct edge. So from A to B, it will be A, B, D. A will contain B, D. This is the adjacency list. B will have C and F as its neighbor, only directed edge and direct edge. Okay, C will contain E and G. Okay, E and G. C will contain E and G. G will contain E, only directed edge and direct edge. E will contain B and F, and similarly F will contain A and D will contain F. Okay, this is the adjacency list. Now what we'll do, just follow me. Okay, listen carefully. We have to take two queues. BFS uses queue data structure. Okay, if the queue data structure, we have taken two queues. First one will contain the nodes which which are yet to be processed. First Q1 will contain the initial node, that is A over here. We are starting from A. This starting node can be changed also. It can be given in the question. It can be taken by you also. There's no hard and fast rule of the starting node. Okay, you can start from anywhere. You have to follow the sequence. How I am doing, just check it. Okay. For starting node A, and initially Q2 is null. Fine. Q2 is null and Q1 is containing starting node. Now what we will do, we will put A, we will check the adjacency list of A which are containing B and D. B and D here are the neighbors of A. That's why Q2 will contain A and B and D will be contained by Q1. Neighbors will be contained by Q1 and which node is processed will be contained by Q2. Processed means we have checked all the neighbor nodes of that particular node. Okay, we have checked all the neighboring nodes of that particular node. Clear? Fine. Next in the queue is B. So we have to check of all the neighboring nodes of B. Which are they? All the neighboring nodes of B. B has C and F. Okay, B has C and F. So we are putting C and F in the queue. Okay, and we are putting B in the Q2. B is processed. Processed means all the neighboring nodes has been checked for that particular node. Next is in the row is D. For D, only F is there. D has only one neighbor which is F and which is already in Q1. So we don't need to put another F. That will be redundant data. That will create confusion. That's why A, B, D will be there in the Q2 and Q1 will contain C and F. Clear? Now after C and F, now in the row is C. We have to process C. C is having two neighbors, E and G. So E and G will be added to Q1. See, step number 5, we have added E and G in the Q1 and C is added to Q2. C is already processed. Next, E has the neighbor B and F. B and F. E has a neighbor B and F. B is already in Q2. That means B is already processed. So we don't need to worry about that. Any node that is already in Q1 or Q2, We don't need to worry about that. We don't need to put that again. We just move forward. So B and F is already in Q1. So we'll just check this F, and F is already in Q1. So we don't need to put F again in Q1. So finally F is E will be put here. E will be put here. A, B, D, C, E, F in the Q2. Next, the last node in the Q1 is G. So G has only one neighbor, I guess, E, which is already processed, already in Q2. So we'll put G in the Q2 and Q1 is null. So we have started from Q1 and Q2. Q2 was initially null and Q1 was containing the nodes. And now when we have ended, Q1 is null and Q2 is containing all the nodes. That means all the nodes has been processed and the sequence is A, B, D, C, F, E, G. This is our breadth first search sequence. Okay? Clear? This is our final output. This is how breadth first search is done. Now, another one traversing algorithm is there, that is depth first search. We'll directly take the example so that you can understand. Mainly you have to do, for any graph you can do breadth first search or depth first search, but breadth first search uses 2Q data structure. Depth first search will use stack data structure. Okay. For depth first search, here's the graph. I have started with node H. Again, there is no hard and fast rule of starting. Okay. We can start with any node. Let it be A, D, whatever. It can be written in the questions also. Okay. So for H, we have the neighbor A. What we have to do is, we are using a stack. So first we will push H. We will push the starting node. Just listen carefully. We will push the starting node H. We will check the adjacency list. H is having the neighbor of A. Then we will print H and push A in the stack. First we will push H. We will check the adjacency list. How many neighbors are there for H? Only one, A. We will print H, then push A in the stack. Now top of the stack is A. We will see the adjacency list A, which is having B and D as its neighbor. So we will print A, and then B and D will be pushed in the stack. Okay. Now top of the stack is D. We will print D. Before that, we will check the adjacency list. D is having F as its neighbor. We will print D and push F in the stack. Now, what is the top of the stack? That is F. So, we will check again the adjacency list. F is having one neighbor, that is A, which is already processed, already printed. Here, previously we were keeping count on Q2 and now we are keeping count on the printing list, printing sequence. Already A has been printed, so no need of pushing A in the stack again. Okay. So, then F will be directly printed. Now, new top of the stack is B. So, what is the neighbor of B? Neighbor of B is C and F. Among C and F is already printed. So, we don't need to worry about F. Okay. So, we need to worry about only C. So, C will be pushed in the stack and printed will be B. So, first we have pushed H, checked the adjacency list. A is the neighbor, pushed A and print H. Okay. H, A, then A's neighbors were checked, A was printed. Then the neighbors were printed, D was printed, neighbors of D were pushed in the stack. This is how it goes on. Okay. Now, the top of the stack is containing C. The neighbors of C is E and G. So, E and G will be pushed in the stack and C will be printed. Okay. This is how it goes on until and unless the stack is empty. Now, E and G is the top of the stack. So, we have to print G and check what are the neighbors of G. What are the neighbors of G? E and H. See, E is already in the stack and H has already been printed. So, we can consider it that H, we need not to worry about no more further, neighbors. That's why G will be printed. And now the last top of the stack, we are saying that last, maybe he has some other, the computer doesn't know about the structure of the graph. It will check the list again for E. For E, it is checking B and F. Already both of them are processed. B and F are processed. Clear? B and F are processed. So finally, print E. We will print E, and hence the printing sequence, how we have printed, that will be our depth first search traversal. So I am repeating it once more. First, what we are doing, we are creating the adjacency list. We are pushing the starting node H in the stack and processing the adjacency list, checking how many neighbors are there of H. There are only one neighbor, A, printing H, pushing A in stack. Okay. Next, neighbors of A are checked, print A is printed, H, A, two are printed. Printing sequence is our output, and in stack B and D will be pushed, neighbors of A. Now new top of the stack, every time we are processing new top of the stack. B and D is the top of, B and D is pushed in the stack, D is the top of the stack. So we will process D, we will check how many neighbors are there. Only one neighbor according to the adjacency list we have made, that is F. So F is here, F will be pushed in the stack and D will be printed. Now new top of the stack is F, F will be processed. F has no new neighbor, F has only A as its neighbor, which has already been printed. So no new neighbor is there, no need of pushing in the stack. So print F. Okay. After printing F, what is the new top of the stack? B. B is the top of the stack. We have to check the neighbors of B. What are they? C. C is the neighbor of the B node. So B node is containing C as its neighbor. B will be printed, and now the new top of the stack is C. C has a neighbor of E and G. We have checked in the adjacency list, and we have printed C here and pushed E and G in the stack. Now G doesn't have any new neighboring nodes which hasn't been processed yet or printed yet. So that's why we are printing G. Next, the top of the stack is E. E also doesn't have any new neighbors, so we are printing E. So this is our printing sequence, and this is our final traversing. This is DFS. What we were doing on BFS, we were taking two queues. First of all, we were taking two queues. One was null, Q2 was null because no nodes has been processed yet, and Q1 was containing only the initial node. After containing the initial node, we will check the adjacency list if it is having any neighbors or not. Okay. B and D is a neighbor. Clear? So we are we are inserting B and D in the Q1, and Q2 will contain A. After B and D, B will be processed. We will check how many neighbors are there for B. C and F are the neighbors of B. So C and F will be processed further. That's why it is inserted in Q1 and B is inserted in Q2. Next in the row is D. D is having only one neighbor, which is F, which is already in Q1 existing. So no point is inserting a new node of F, already is there, right? F is already there. So we are inserting D in Q2 and C or F is remaining in Q1. Next is C. C is having E and G as its neighboring nodes. E and G will be inserted in Q1 and C will be inserted in Q2. Processed. Processed means every time you process any node, just remember processed means checking the adjacency list about the neighboring node. Checking the node in the adjacency list for the neighboring nodes. It is called the processed one. Okay. And next, F is there. F has only one neighbor, which was D, I guess. Let's check the adjacency list. F has A. A is already processed, so no need of no point of inserting A in the Q1 already. Okay, what if the graph is not directional? For directional, only BFS and DFS are done basically, because otherwise you will fall in the loop. For directional graph, until and unless it's a directional graph, we cannot go for BFS and DFS, because if it is undirectional, every time we are going, okay, Google form, you don't have to worry, I'll give you another link. Okay, just wait, I'll give you another link for Google form after the class. Just follow me, Harshita, that if, why are we starting with, I've told you I have started with H, you can start with A as well. There's no hard and fast rule to follow the starting node. The starting node can be given in the exam also. Okay, starting node can be given in the exam also. So if the graph is not directional, then you will fall in the loop. You cannot get over it, right? If the nodes are processed, then there may be a chance. It has to be a directional graph, so no need of worry about that. Okay, is it clear, Harshita? I hope it's clear. So finally, E and G are there in, okay, E and G are there in Q1, and Q2 is containing A, B, D, C, F. Next is E. E is having the neighbor B and F. B and F. So B and F is already processed. So we know we don't need to put it once more. So E will be printed here, not printed, pushed here, Q2, and G is here. G is not having any new neighbor, so that's why G is also been here. Okay, this is our final traversing of the graph BFS for this graph. So I hope it's clear to everybody. Okay, and Harshita, one more thing I would like to say, if it's an unidirectional graph also, if the nodes has been processed, suppose we are processing A, B, C, D, if the nodes has been processed, so no need of reprocess the node. If a direction is there, maybe neighbors are there. Suppose this list, if we consider this one, this is an undirected graph, and if we are considering this, when we are starting with A, we are considering B and D. When we are considering B, we are having A, D, C, but we are seeing that A has already been processed and D has been inserted. So we will consider C only. We will insert C in the Q1. So no need of worrying. If it is undirected or directed, doesn't matter really, right? If you have to check if the node is processed or not. If it is processed, then you don't have to worry about it. If it is not processed, not inserted, you have to insert it. Clear? I hope it's clear. So I'll be giving the attendance list once more in the Google, Google form link in the Telegram group after 5 to 10 minutes. Okay. So I'm just stopping my streaming right now. Already it has been 12:19. Thank you for all for the classes. I hope there's no more questions are there. Okay, understood everyone? So I'm stopping the live streaming. Okay, thank you.